Welcome to tonight's BA webinar. We're broadcasting on Zoom with a live stream to YouTube, and the recording will be available to watch on our YouTube channel shortly afterwards. You can ask questions during the session by typing them into the Q&A on Zoom or on the comments in YouTube, and we'll answer them at the end of the session. It's my pleasure to hand over to the BAA President, David Arditi.
Thank you very much, Andrew. Nice to have you here for another BAA webinar. And we haven't really covered the moon very much in our series of webinars, so we're putting that right today with this intriguing title of Backyard Lunar Mineral Prospecting. Mark Kidger, you may well have seen before. He's given many talks to the BAA. He's an enthusiastic member as well as a distinguished professional astronomer. He's currently employed by the European Space Agency. Last time he gave a webinar to us, it was on the subject of Betelgeuse, the star in Orion, whether it would explode as a supernova soon and what we would expect if it did that. But today he's dealing with a subject much closer to home in collaboration with his friend Juan José Godoy Carrera. And Juan is a member of Madrid South Astronomical Society. He is an amateur astronomer, and he's also an officer in the Spanish Navy. And he's a serving officer. So maybe we'll learn more about that and how he became interested in the subject of lunar geology. So without further delay, I will hand you over to Mark and Juan.
Okay, thanks very much indeed, David. So this talk, as you say, it's an intriguing title. It was a complete accident. Some months ago, Juan José sent me some lunar images that he'd been processing, and I was intrigued by them. It was on a comet observing WhatsApp group, and we sat down and started to talk about them, and a paper came out of it for the BAA journal, which I think is soon to be published. And then a second paper appeared, and there may even be a third one at some time in the near future. So the subject is just what an amateur astronomer can do with backyard equipment that it takes NASA hundreds of millions, sometimes tens of billions of dollars to do. And the curious thing is there is an enormous amount that an amateur astronomer can do for original lunar research using normal equipment that most amateurs do have. So why today? When I was offered the chance to do the webinar, I looked at the calendar, and of course, today, 53 years ago, Neil Armstrong was standing on the ladder of the lunar module. He then jumped down and stood on the landing pad and finally took a step off the lunar module into this strange alien landscape that is the moon. Now, of course, Armstrong and Aldrin, what they did was that they explored not very much an area of oblique lava plain that was actually deliberately chosen by NASA to be as boring as possible. They wanted it to be a safe landing site. You can see on the left, these are lunar reconnaissance orbiter pictures, a sequence through a lunar day. You can see the lunar module, you can see its shadow, you can see at different times of day, the footprints that Armstrong and Aldrin made. To the right, there's Armstrong's solitary trek to the crater, this mysterious trek down to the below the bright points. Those are the lunar surface landing experiment package, the instruments. And to the northwest, you can also see some trails, some dark trails, which is where they took samples. What you don't see on these images is the flag, because the flag actually fell down as the lunar module took off again. Now, there are only 2 flagpoles that actually are still standing on the moon. We know that from the Lunar Reconnaissance Orbiter pictures. Now, I said that the Apollo 11 landing site was boring, but actually, when the samples came back, they turned out to be exceptionally interesting and very, very surprising to the scientists, because they were extraordinarily rich in titanium, far richer than Earth rocks, in fact, by a factor of about 10 or 12. In fact, we know that Mare Tranquillitatis, where they landed, is the area of the moon with the highest percentage of titanium anywhere on the lunar surface. There are places in the northwest of Mare Tranquillitatis that reach 12% titanium, which is really quite extraordinary. For comparison, on Earth, Earth rocks are about 0.5%. So you might think that it was actually an accident that the astronauts landed at this geologically very unusual site. But actually, that's not quite true, because before the sites were selected, NASA took images of the moon using red and blue filters. That was about as sophisticated as they could get. And they were aware that some of the areas of the moon were quite red. For example, the Apollo 12 landing site in Oceanus Procellarum. And they knew that Mare Tranquillitatis and also the backup landing site for Apollo 11 in Sinus Meridi were very blue, but they didn't know why. And so they actually picked the first 2 landing sites so that they would presumably be of different composition. And so if for any reason Apollo 11 had been delayed for about 5 days in launching, they would have gone to Oceanus Procellarum, what was eventually the Apollo 12 landing site. And Apollo 12 would have been switched to the Mare Tranquillitatis site. That was the plan. So it wasn't completely an accident that the Mare Tranquillitatis site was particularly different to normal. They knew there was something about it. And now, 53 years later, if you're an amateur astronomer with pretty standard equipment, you can take images like this one. This is one of Juan José's images, Mare Imbrium, that can analyze these tiny color differences that NASA first detected in the 1960s. And you can observe them in far more detail than was ever possible 50 years ago. And in fact, using calibration from the various lunar probes that observe the moon from orbit, you can actually study in great detail, and I really do mean in great detail, the composition of the lunar surface from the comfort of your armchair. So now this is where things start to get complicated. I'm going to pass over to Juan José, who's in Toledo, and ask him to explain to us how you can obtain these images that tell us about the composition of the lunar surface. So I've just stopped sharing. Juan José, all yours.
Hello, everybody. Thank you very much. My English is not well. I'm sorry by that. A ver si puedo.
If you have problems, Juan José, I can put up the presentation again. So, and you tell me when to change slides.
Okay.
What you should see is a green share button, usually kind of around the middle in the bottom.
With an arrow pointing upwards.
Compartir pantalla.
That's it. Well done. Now put it in full screen mode.
Can you see?
Yes, we see.
I'm sorry. Okay. This is my summary. I am going to explain this summary. 5 steps. This is the order to get lunar image 2. Number 1, equipment. Mount. My mount is this. German Equatorial. Everybody know Mount Equatorial, I think. The question is, can you use altizimutal mount of dot zone mount? I think yes. Optical tube is better than refractive optics. This is my optics tube, Newton types. Okay. This is my camera. Is especially for planetary images. Can you see? Can you see technical data here? For example, high quantum efficiency, especially for green zone. Preferably pixel density, height, or small pixel in CMOS sensor. Filters. Only needed RGB filters. Okay. Filter L is not necessary. Only RGB. It's filters well is optional, okay, but no necessary. Step 2, capture, video capture. Capturing video is necessary if you want to get a quality image. A lot of frames is good for stack later, sorry. Can you see ASI Studio? It's software easy. El fish icon can I use for capture video. Step 3, stacking, and step 4, processing. Both I use astrosurface stacking and processing software. Video frames are stacked AVI or SER, okay? Stack result file is TIFF, and TIFF file is processing with astrosurface again. Finally, I use GIMP. All software is free. Capture, stacking, and processing. This is GIMP, software GIMP. The GIMP alternative is Photoshop, but GIMP is useful. With GIMP, color saturation, invert colors, and transformation histogram. Next slide is a video, okay? In this video, open GIMP, open files, imagine moon, and natural colors. Number 1, menu color auto white balance. Number 2, menu color, always menu colors. Color saturation again and again. Strongly. Save image here. Save image here. Then invert. Then fit histogram. Summary, last video. Number 1, white balance. Number 2, color saturation. And again, color saturation. 2 or 3 times color saturation. Save image here. Invert colors. And fit histogram. And save image here. This is Mare Tranquillitatis image, natural colors. It's a good image. This is Mare Tranquillitatis, enhanced color. Can you see details better of minerals? Can you see Mare Tranquillitatis, inverted colors? Can you see better minerals of titanium?
So I'm going to share the screen again. I should say Juan José has never, ever tried to give a talk in English before. He deserves an applause at the end.
I'm sorry.
You've got to stop sharing, Juan José, because I can't share yet.
Great. That was a great little presentation there. Thanks. I can, if necessary, I can stop the sharing if you want from here.
If you, well, it might be the quickest thing, Andrew.
There you go.
Right, well done. So now
thanks very
all
much, Juan José. That's fascinating.
Get my talk back. Right, so these images give us a huge amount of information. So even the black and white image, or what appears to be black and white, because the image on the right is actually the natural lunar color. It is a genuine RGB image with the color as an observer would see it. Gives a lot of information. You look at the density of craters across the Mare Tranquillitatis, and that gives you the age. And you can actually work out the age of different regions from the number of craters and the size of craters. The left-hand image, where we've got the color enhanced. You can tell from the colors that the Mare is made out of many different what are called geological units. You can see areas of light blue, you can see areas of navy blue, areas of brown. There are many different shades and colorations. There's some light black brown. There are areas that are white. And what that tells you is that this whole area of the Mare, many different geological processes have been going on over the history of the moon. Now, there's a good reason for that, and that is that Mare Tranquillitatis is a lunar anomaly. It's a very strange sea. It's the oldest of all the lunar maria. That's now pretty well established. It hasn't got a mask on. Now, the younger astronomers here may not remember mascons, but when I was a kid, there was a lot of talk of mascons. Stands for mass concentrations. They're gravitational anomalies that exist in the center of all the lunar seas apart from Mare Tranquillitatis. And they were thought to be a serious menace for spacecraft orbiting the moon, because it was feared that they could actually pull a satellite or a capsule out of orbit and cause it potentially to crash. And another thing that makes Mare Tranquillitatis absolutely unique is it's not even a basin. And you can see this is laser altimeter study of a laser altimeter map of Mare Tranquillitatis. You can see the west hand side is depressed. Whoops, shouldn't have done that. It's depressed a bit. But the east of Mare Tranquillitatis is actually a high plateau which reaches what we call the lunar mean datum, or basically sea level on the moon. And in fact, in some areas even gets a little bit above sea level. So the whole of the eastern side of Mare Tranquillitatis is a huge plateau. And if you walked across Mare Tranquillitatis from west to east, you would really be climbing a quite appreciable slope a lot of the time. The other thing you notice is Mare Serenitatis to the north is much deeper. It's more than 2.5 kilometers below mean datum, below sea level, if the moon had seas. It's much deeper than Mare Tranquillitatis. And we can actually see this in the fact that it appears that some of the lava from Mare Tranquillitatis has flooded down the slope north into Mare Serenitatis. Now, if we put up this image of Mare Imbrium again, because it is such a spectacular image, and it's the lunar sea that has the most remarkable range of colors when you enhance the colors. You can see most of the minerals that on the lunar surface. So anything that's light blue, for example, is fresh, unweathered material. It's lunar mantle that's been exposed relatively recently, hasn't been weathered by radiation. It's high in aluminium. Anything that's navy blue, up here, for example, you can see Sinus iridium splits neatly in two. The left half is dark, the right half is much, much browner, much brighter. Navy blue is high titanium basalt, high titanium lava plains. In fact, the Chinese rover Chang A3 landed almost exactly on that divide, just on the left-hand side, and it sent very spectacular images of the way that the color of the Sinus iridium changed remarkably, very, very abruptly. Anything that's dark brown, like this, and some areas are almost chocolate brown, that is very high in iron. The browner it is, the richer it is in iron, which is something that actually you see on Earth as well. Reddish rocks or red-brown rocks, they're typically high in iron. And again, it's lava plains, but it's iron-rich basaltic lava. Then you have these light brown areas, the highland areas. For example, here. This is also high in aluminium. It's material that was thrown out when the Imbrium Basin and other craters were formed. Again, very high in aluminium, highland material. And finally, something that you find in just a few areas on the moon, Aristarchus, the plain here, the plateau close to Aristarchus is one example. And also the western edge of Oceanus Procellarum, you find yellow and red colors. Now, I actually remember watching Jack Schmitt looking at those rocks on the moon and saying, it's orange, crazy man, in Apollo 17. And the astronauts were very excited because they thought they'd encountered a recent fire fountain, a recent active volcanic vent on the lunar surface. It turned out that it wasn't. It had burnt out 350 or 3,500 million years ago. But these red and yellow colors tend to be pyroclastic glass beads, so volcanic glass. That was what gave the orange color to that soil in Apollo 17. So you can see that with an image like this, you can find all kinds of colors and you can look at minerals. You also see that down here, quite close to Copernicus, there's another area, very, very dark blue, very rich in titanium. And these areas haven't actually been really very well mapped. There have been some papers using data from the Chandrayaan lunar probe, from the Lunar Reconnaissance Orbiter probe, but nobody's really mapped these titanium-rich areas in detail. So there's actually a nice project there for somebody who's interested in doing some really serious lunar research, thinking about the fact that we will be returning to the moon in the next few years, and we'll be looking to exploit it for resources. However, we've got a problem with this because the titanium-rich basalts, they are navy blue, and really the eye is not good at distinguishing different tones of navy blue. In navy blue is navy blue is navy blue. On that image, I can't really very easily distinguish what is very dark blue from what is just dark blue. And that's where this inverted color comes in. Because if you invert the colors in the image, navy blue turns into orange, which is what Juan José was showing earlier. And it turns out that the lighter the shade of orange, the higher the abundance of titanium. So basically, the lighter oranges are where the blue is really dark. So if I can get my cursor back, and it doesn't, there's an area here, for example. This area is about 12% titanium. And you can see it's clearly much lighter than the area around here or the area around here. Down here, it's actually bluish gray. That's high titanium, but it's much lower titanium than the regions in the north. And just by looking at the colors, if it's orange yellow, you know it's 10, 12% titanium. If in this process it comes out orange red like this, you're about 6 to 8% titanium in the rock. And anything that's gray here, this is a bit lower, it's probably 4 to 6% titanium. And anything with a bluish tone is below 4% titanium. Fine. So what's the proof of this? Well, it turns out that one of my colleagues, he's only 3 doors up the corridor, actually published a paper using data from Lunar Reconnaissance Orbiter, which observes the moon in 250 filters, not in Juan José's 3, and calibrated very carefully the titanium Bunsen in Mare Tranquillitatis. And we can actually use this data. I can use the plot from Sebastian's paper to calibrate Juan José's image. And here I've put them. I've tried to orientate them the same way. Of course, Lunar Reconnaissance Orbiter was able to observe Mare Tranquillitatis from above, whereas from Earth, it's always a little to the edge of the disk and a bit distorted. And I've tried to orientate them so that the orientation, the size is just about the same. And you can actually correlate very nicely the scale at the right, the color, shows the level of titanium as determined by Lunar Reconnaissance Orbiter. These red areas here, this is nearly 12% titanium. And you can see how beautifully it corresponds with the yellowish area that Juan José has. You can see other details. This area, which is much lower titanium, captured absolutely perfectly. These structures here, again, low titanium areas, again, absolutely perfectly captured. And the Apollo landing site, which is just about here, it's actually quite modest titanium. They'd have got an even bigger surprise had they landed up in this area. But even this down here, 6% titanium, that was a huge surprise for the scientists. So it turns out just by using this calibration from Lunar Reconnaissance Observer, applying the corrections that Juan José has done, you can say if an area of the moon is between 10 and 12% titanium, and you can distinguish that clearly from an area that's between 8 and 10%, between 6 and 8%. And I find that absolutely amazing that a backyard astronomer with quite simple equipment that any amateur astronomer can purchase reasonably cheaply, can reproduce, and probably even with better resolution, the results of this NASA probe that cost hundreds of millions. I haven't checked exactly how much it cost, but for ESA, the probe that I'm deputy project scientist on, it comes in at about £180 million. And that is a very, very cheap interplanetary mission. That's Comet Interceptor. So when I saw this image, this was what made me really excited. It was a late night WhatsApp session with Juan José. That I just thought that was absolutely amazing. The beautiful correlation between his RGB images and a lunar probe that's cost hundreds of millions of dollars. So just to finish, a quick summary. So normal color images, even when you enhance the contrast, you don't get very much information on composition. You can see that bright areas are young. You can see very dark areas are probably rich in titanium. But that's about as far as you can do. If you color enhance the images, you really can start to reveal a lot of basic compositional units. You can pick out the aluminium rich, the iron rich, and the titanium rich areas. You can see what is fresh unweathered rock, and you can really pick out what are the youngest craters. Something like Aristarchus there, you can see how blue it is compared to Copernicus. Aristarchus is clearly younger than Copernicus. And you can also even pick out areas of ancient volcanic activity, fire fountains. You can map the different lava flows, because lava flows came out that were very rich in titanium. Sometimes they've been covered by other lava flows more recently. Sometimes they've been covered by material excavated from lunar impacts. And the most amazing thing for me is that just with these color enhanced images and by inverting the color, you can estimate the abundance of titanium in the lunar surface with good resolution to about plus or minus 1%. So I don't know how long we've taken, but with that, thanks very much to everyone for listening. And I think we'll open this for questions. And as I said, this is the first time Juan José has tried to give a talk in English. I think he did extremely well. So thanks very much, Juan José, and keep observing the moon. And keep sending me images late at night on WhatsApp.
Thank you, Mark, and thank you, Juan José. Those are both fascinating talks. We also have Dr. Tony Cook on, the director of the BA Lunar section. So I'm just going to promote him to a panelist as well. So Tony, that should be happening now. And just while we wait that to happen, just to let you know, I've had a couple of internet glitches with my router whilst you were doing that. Thankfully, only lasted 30 seconds. But if I suddenly freeze or disappear, then that'll be what's causing it.
Thank you. Thank you, Juan José, for talking in English to us. You did an excellent job. Really, really splendid.
We did have a plan B that he would speak Spanish and then I would do simultaneous translation, but I'm very grateful that he managed to soldier on.
It's better to hear it from the horse's mouth, as they say. It's an English expression.
Yeah, and it was fascinating to see, and also kind of the detail and how stark the contrasts were, how you could really tell those lunar minerals from those tricolour images. If anyone wants to ask questions, just to reiterate, put them in the Q&A on Zoom or in the comments on YouTube, and we'll read them out. We haven't got any questions yet, but we have a comment from Peter Carson, which was to thank Juan José for presenting in English.
I'll make a comment that it's possible to do this process either with color cameras, in other words, something like a DSLR, or a color CMOS camera like the ZWO cameras, or to do it by Juan José's method using a monochrome camera and RGB filters. And I was just wondering about how good these methods are. I would expect that the RGB method with the mono camera to be better, to give better discrimination, but you can get quite similar results with the color camera as well.
Yeah, my doubt about that, David, would be how easy it is to calibrate the color camera, because with filters, you know what light you're putting in, and you know what the response of the detector is. I'm a little bit suspicious of color CCDs, but that might just be my background with scientific detectors.
Mm.
I don't know if Tony has a comment on this, because Tony, of course, was the referee for our first two papers, and he knows he's been threatened with a third paper at some time.
Yeah, you've got to be a little bit careful with cameras, particularly to make sure they don't leak in the near infrared. So always use a infrared blocking filter on there. Might be worthwhile pointing them at some standard stars where you know the color magnitudes, just to calibrate the cameras properly. Might be an idea.
Yeah, I think people in the variable star field have the same kind of debate as to whether they can use color cameras or not. And I think it is possible to calibrate them, but it requires work.
Yeah, exactly. It's an extra stage of difficulty in the process. So, which is why I think if you want to make life easy, it's best to do it with the RGB filters, because that is easier to calibrate. and you've got more control over what you're doing.
We have a question from Tony M, or I think it may be MSAS, and he's asking, do the RGB filters have to be narrow band pass for best effect?
Did you understand the question, Juan José? Do you want to try and answer?
Can you translate, please?
Well, ok. Me pregunta si tiene que ser banda estrecha o banda ancha los filtros.
Los filtros. Bueno, estoy capturando en la zona de luz visible. Entonces, cuando se unen yo hago 3 capturas de la misma zona y no lo he explicado, pero hay que unir los 3 canales para fusionar los 3 colores y luego ya obtengo una luz, o sea, perdón, una imagen color natural. Pero no estoy, o sea,
Pero usas banda ancha. You use broadband filters.
Es banda
not
ancha,
narrowband, because you want to match to natural light. Yeah, so what Juan José was saying, what he uses broadband filters because he's trying to match to the natural light. So he's got filters that actually cut off very sharply. They barely overlap at all. And the idea is to capture most of the band of white light, but to separate it clearly into colors. So he does use broadband filters. Narrowband filters you can use, but you might have some quite unusual effects because you're throwing away quite a lot of the light in the gaps between the filters. So I'm not sure how the images would come out. The other thing Juan José said is that obviously what he does is he does a video sequence through each filter. So typically he'd integrate for 10 minutes in blue, then 10 minutes in green, and then 10 minutes in red. And then he has to combine those 3 sequences and pick out the best images in each band to combine to get the color image.
Interesting experiment to try narrowband filters, wouldn't it? I've never tried that, but it could be done.
Yeah, it could be, and that's exactly what the Indian Chandrayaan probe do, or the Lunar Reconnaissance Orbiter. They use the equivalent of hundreds. In fact, in Chandrayaan, they could choose up to 500 bands, equivalent to 500 very narrow band filters in the near infrared to pick out different minerals in the lunar surface. And that is the advantage. When you've got a few $100 million to play with, and you can do things that probably aren't open to Juan José or to anybody else on here, but it'd be an interesting experiment, and it's actually what these lunar probes are doing, but on a much, much larger scale.
And we've got a couple more questions come in. I'll start with the second one first, because it relates to what we've just been talking about. And this is, again, a follow-up from Tony M. And he's saying his old RGB filters leak into each other's band pass, very similar to the Bay filters on his DSLR.
Right. Let me go back a few slides because, come on. It's going back slowly. Okay, I've got to wait for that to come up before I can't get it to go back any further. I wanted to go back to the slide where we've got his band passes. There you are. You can see that actually there's very little overlap between these Barda filters. The blue and green do overlap to a degree, but the green and red, they've hardly got any overlap at all. You can see they only really overlap where the sensitivity is extremely low. Blue and green a little bit more. So these are actually pretty good filters to use, broadband filters to use for this kind of work. You can see here, this is the point where blue and green start to overlap. So the CCD is fairly sensitive, or the CMOS is fairly sensitive there still, but there's not much overlap. So it's a matter of finding a manufacturer that produces the best quality filters. The old RGB filters, which were glass, they were not very good. They really did overlap quite badly, and they gave these broadband filters quite a bad name. But now there are much better broadband filters that are available.
Yes, I've got the Astronomic series of filters, and they publish a graph like this, which looks very similar with a square cutoff. But you can tell with the older filters, when you look through them, just look at a white piece of card through them and compare them with how a set with a genuinely square cutoff looks. The colors are much purer, and generally the green in the older filters looks more yellow, because it's a broader band. So if you get a pure green through the green filter and a pure looking blue, you can pretty much tell by eye how good they are.
If you see yellow through the green filter, that's because there's a lot of blue light coming through. And the blue is mixing with the green and making yellow. So yes, and I have to admit, when I started observing in La Palma, the Captain telescope, which is the one I observed on most, the 1 meter, that had glass filters, and they got rid of them quite quickly. They changed those for a better set a few years later, because they were not particularly good filters. Amateur astronomers these days have the sort of equipment that we could only dream of when the observatory on La Palma was set up. If far better CCDs, far better filters, far better electronics, and the computers, the computer I was using, we could save 8 350 by 512 CCD images on disk before the disk filled up and you had to stop for 5 minutes or so and save everything to magnetic tape. Now that's amateur equipment now really is almost indistinguishable from the professional equipment of about 10 years ago. When amateurs catch on, they will start really doing amazing things, as Juan José is doing.
We've had a question about minimum aperture of telescope from Clive Morris. Asks, what's the minimum recommended aperture? Size of telescope.
Okay, hello Clive. Juan José, ¿entiendes? Tú tienes de 20 centímetros. ¿Cuál es el mínimo que recomiendas? He's looking puzzled.
No lo sé, realmente no lo sé, porque es mi único telescopio. Jessica tiene uno similar. El mío es de 10 pulgadas.
Okay, so he's got a 10-inch, 25 centimeters. His wife has a similar telescope, so he's not tried with smaller telescopes. I'm quite sure that you could do this with a 20-centimeter telescope, an 8-inch. A 6-inch, you may be pushing it because you do want to have resolution. And with the filters, you also need light grasp, because one of the things that Juan José does is he's taking 50 frames per second through the filters to freeze the seeing as well as possible. Now, if you have a smaller telescope using filters where you're cutting down the light and you have to start decreasing the frame rate, then you don't get rid of the seeing so effectively. So I think it might be possible with a 6-inch, a 15-centimeter telescope but 8-inch, 20 centimeters probably would be better, just because it allows a faster frame rate with really good signal to noise.
Yeah, my experience is the bigger the better, for the reasons that Mark says. You can do it with a 4-inch telescope and you'll get nice results, but they won't have as high a resolution as we've been seeing today.
And that's the trick. You really want to get fast frame rates to freeze out the atmospheric seeing as much as possible.
So we've got a question from Simon Street. Are there any other metals that are detectable by this method other than titanium, iron, and aluminium?
Right, that's a good question. Those are the big three in the moon. As with silicon, they form more than 90%. Sorry. Yes, that's right. More than 90% of the lunar surface. No, there's a lot of calcium. I haven't experimented at the moment to see how you can detect calcium, but I guess that would be something for the future. That one, the calcium minerals, they are not quite so obvious in the visible, I believe. So I would have to have a look at that. Most of the papers that are published looking at lunar mineralogy do look at these big three elements. And silicon, of course, there's a huge amount of silicon in the lunar rocks, but the silicon goes with the aluminium. Where you've got rocks rich in aluminium, you've got rocks rich in silicon. It's basically normal silica dioxide. So you can't really separate the two very easily. Silicon is just everywhere in the moon, and it really, there aren't huge differences from one place to another.
John Dunthorne asks, is what we're learning here giving us an indication of what valuable minerals might be present on the moon that could be exploited in the future?
There is a reason why the first lunar mission for many years that NASA launched was called Lunar Prospector. And it was looking precisely at this. It was looking for radioactives, and it was looking for minerals like iron, exactly that. And it was all in the name. They were looking for areas that could be exploited. And the fact that titanium, which is very much used in aerospace, it's fantastically useful because it's very light and extremely heat resistant, is so prevalent in some areas of the lunar surface. That makes them prime territory for exploitation, for mining. And of course, the one thing that we can't do, we can't look for hydrogen, for water, that you find in the lunar poles, unfortunately. But again, it is no coincidence that both the Americans and the Chinese have said they're planning to land at the lunar South Pole, because that's where the water is.
Strangely enough, my PhD was on titanium. It was such a long time ago, I can't remember much about it, but I do remember that titanium is very evenly distributed in the Earth's crust, and that's why it's expensive to extract, because you have to mine an awful lot of rock to get some titanium out of it, because there's a lot of titanium in the Earth, but it's very evenly distributed. Exactly,
it's about 0.5% average, but you're looking, that area of the north of Mare Tranquillitatis, it's 12% titanium. That is absolutely incredible quantities.
So
now that's that. If I were a lunar mining prospector in 20 or 30 years' time, that is probably one of the areas I'd be looking at.
Stake your claim now.
Yeah, exactly. Well, you know that various Japanese corporations such as Mitsubishi are already talking about the possibility of establishing mining operations on the moon. You've got lots of silicon, which you can use for solar panels and for generating electricity, lots of free sunlight. You can extract these minerals very, very easily. And there's more than one science fiction writer who's been talking about possibly in the future, ecologists won't be trying to stop mining on the Earth. They'll be trying to save the last few virgin areas of the moon from mining operations.
And indeed, I remember hearing a talk at some conference about the legalities of this and the question of who owns the moon and who has the right to exploit it. I think it's a pretty grey area, actually.
It is. There's the International Space Treaty, which just states that nobody can lay claim to anybody. So the Americans can't, or the Chinese can't say the moon is ours, nobody else is allowed to land. But there is nothing in that treaty that stops you exploiting the resources in any way you wish. And we all know things like the Antarctic Treaty. As soon as it becomes possible to exploit the minerals, it's very likely that they are going to be ripped up immediately.
I noticed we have another question from Steve Knight, who pointed out that some BA members have a paper published on doing polarimetry for mineral analysis on the moon.
Sorry, I didn't hear the first part of the question very well.
So what it is, what he says is, are you thinking about doing polarimetry for mineral analysis? As some BA members have got a paper published on the technique applied to the moon.
I am not thinking of it, although we had a seminar a couple of, 2-3 weeks ago. A scientist who who works at the European Space Technology Center in the Netherlands, who is using polarimetry to study the properties of the surface materials and the granularity of the lunar surface in Mare Tranquillitatis. It was an absolutely fascinating talk, and he was actually able to get his hands on some of the samples brought back by Apollo 11. And his talk was about how they took these little samples of dust and processed them and used polarimetry in the laboratory to study the properties of this dust and compare it with the properties of the lunar surface. That is also a very rich area for study. Polarimetry tells you how the light changes when it's reflected, how it's polarized, and it's a very little exploited area of astronomy. There's not a lot of polarimetry done by anybody, and that's another very rich area for exploitation. Surface properties.
Yeah, I remember we had a talk about this at the BAA Winchester weekend some years ago. I forget the name of the researcher who was exploring this, but it was done with amateur equipment, with the types of telescopes we've been talking about. So I think you could get complementary information. It would be a bit different to the color information.
Exactly, you would. And that's what I'm saying. Amateur astronomers now have got the most phenomenal opportunity because they're using equipment that is absolutely competitive with professional equipment.
Looking on the BA website, I can see it was Andrew Fernside, Philip Masding.
And Andrew has frozen.
Yes.
He did warn us this would happen.
Could I possibly ask a question for a moment to do with the processing? You were talking about inversion of the colors. Could you explain that a little bit more? Is it like 1 divided by red and 1 divided by green, 1 divided by blue? What's going on there? Or is it just like a negative image?
It's a negative image. So let's, yes. I've got the same problem again. The blasted thing refuses to go back because of the animation. So Juan Jose, this one is for you. How do you invert the colors? Como inviertes los colores? So I'm going to put the video working. I'll see if I can stop it at the right place. Let's see. It's fascinating watching this video, how the colors start to appear from what appears to be a black and white image. Even halfway through the processing, you're already starting to see all these colors appear. So there's the inversion. Right. Let me...
I think the question is, what is the mathematics of the inversion, really? And I think it's not what Tony suggested. It's not a division. I think it's a difference that it's doing, but I'm not certain.
Juan Jose, come on, see if you can answer this question.
Sí. Can you speak Spanish?
Okay, you speak Spanish, I translate.
Creo que la pregunta se refiere a cómo invierto el color. Pero
sí, ¿cómo, ¿qué operación matemática representa?
No lo sé. No lo sé, Mark. Está en el menú de, al ser software libre, entiendo que está documentado este software y se puede consultar.
Yeah, I think well, Juan says he doesn't know, but just looking at that image, what we're doing is we're flipping. Where we had red, we've now got blue. And where we had blue, we've now got red. And that's basically the operation that it's doing. And it just turned out, and this was pure luck, that Juan Jose was sat there at the computer one night, and he was playing with some images, and he sent me a selection of them. And I looked at this image where he'd done the inversion, turning red into blue and blue into red. And at this time, I was reading and studying a paper by my colleague on titanium abundance. And his image looked so much like that map. It was my eureka moment, but this was probably about 1 o'clock in the morning. So I didn't shout eureka because the family was asleep. It was just an amazing moment when I saw that image come over the WhatsApp. But that's all it is. There's no great magic to it. The only piece of magic that Juan Jose applies, let's see if I can find the moment. Boy, the only piece of magic is how he modifies the colors, which is here, because he's moving the color scale. And that is the trick. It's that change to make it almost a logarithmic scale, which reveals what is very dark navy blue in the enhanced image, turns it into tones of orange that allow you to distinguish the titanium. So there's no great magic to it. It's all a little bit of trickery, sort of smoke and mirrors, but it just works beautifully.
Well, do you think we should draw a halt to it now, Andy?
I think so. I might just make one final comment, if I might take the privilege, which from my knowledge of the BA spectroscopists, which have slit spectrographs, I wonder if at some point there's something which they might also kind of have a go at. Obviously, it would only be very thin slices of the moon, but the fact that you can see it in these images makes me suspect that things would come out there as well.
maybe you would. Maybe you would. One thing that I am particularly interested in, and Tony knows this, I just wonder if some TLP reports were due to people picking up some of these color differences with the Sartori moon blinks. And certainly there is one very famous lunar TLP where I have very strong suspicions, because there is a color anomaly exactly where the TLP was reported. And as Tony knows, there are areas that were permanent moon blinks, and there's an area in Mare Frigoris. And if you notice the image of Mare Imbrium there are some interesting patches. Now I can't see it because I've got the video in front, but somewhere about here, if I remember rightly, there is a lovely patch of very dark navy blue titanium-rich lava. I have no idea where the moon blink was in Mare Frigoris, but I'd be prepared to bet £5 that it was there. I don't know if Tony knows the answer off the top of his head.
If you've got a couple of minutes, I can look it up for you.
Why not? If there are any more questions, I can see something's appeared on the question and answer. I don't know if that's a new question.
It's more of a comment, really.
Because we're doing science in real time here, David. So
Tony M has commented that GIMP has many color mapping capabilities, so it depends what exactly it's doing under the hood, as he puts it. And John Dunthorne says, is inversion not turning colors into their complements, e.g. blue into yellow, red into cyan, green into magenta? Is that what inversion is? That sounds quite likely to me.
Could be. GIMP is the software that we use here in the European Space Agency for image processing like this, but I admit I've not really got into it. Juan José is much more expert than I am with image processing. I usually spend my time writing technical documentation for missions, which isn't the same as having hands-on data. But it could well be. If somebody comes up with the answer, I'd be interested to know it myself.
Another thing that occurs to me is that if you're studying color and trying to do it in high resolution, you've also got to correct for atmospheric dispersion. Otherwise,
yes,
you get color fringes. And that's possible with a dispersion corrector, which is quite a cheap accessory now for emitters.
Yes, and again, I mentioned TLPs briefly. Atmospheric dispersion, chromatics in the atmosphere, that was probably the source of many TLPs. I know I reported in my misspent youth one TLP myself. And years later, I read a paper about chromatics, atmospheric chromatics, and I realized that what I was seeing was almost certainly false color caused by atmospheric dispersion. And one of the things that we're starting to work on now is doing this process with high resolution images. So Juan José is starting to work on individual craters that are particularly interesting for various reasons that I will be very secretive about for the moment. But we've got 2 or 3 craters we've got on our hit list. And yes, that's one of the things that's going to be a potential problem for us.
It's a thing we deal with in planetary imaging all the time, and you can correct it very finely when you're looking at an object like Jupiter. And you can get in real time, the capture software will produce an exaggerated color version in real time of the actual video. And so you can see where the color fringes are, and you can adjust your a dispersion corrector to completely eliminate them.
Ah, that's interesting. I was not aware of that. I need to start reading more journal articles.
I'm not sure there's been an article on that, but I've just learnt it from people using that technique. And in the fire capture software, which is a commonly used image capture software, that's documented, that method.
I don't hear Tony coming back with an excited answer to the question.
There are three transient lunar phenomena for Mare Frigoris. There's one in 1871 by Pratt. There's one in 1982 by my father, and there was one in 1994, April the 2nd.
Yeah, and what about permanent blinks, though? Because I know there was a permanent blink in Mare Frigoris that people start to see when they use the moon blinks.
Yeah, I'm a little bit uncertain about permanent blinks because I've looked up some of these on the Clementine color images of the moon, and there simply aren't any colors there. For example, there's one in Fractorius, which was notorious for being a colored reddish area seen on a lot of occasions. But when you look it up on the Clementine data, you don't see any red color there. So
yeah, that may be the particular bands that Clementine was using. Red color is very suggestive of volcanic glass. And we know that there are areas of the moon where you find volcanic glass. And I'll tell you for free that one of them, which is well verified by satellite data, is around Gassendi.
all right, okay. I'll go and check that out. So, yeah, interesting.
So that's a sneak preview. Andrew's grinning.
Well, the Lunar section might consider promoting this as a new project, or the polarimetry even as a complementary project.
You know, it's amazing what you can see in these images. So I'm just looking at this image. Have a look at Copernicus. You can actually see differences of color in the middle of the crater. There's an area there which is clearly different color, different composition. Having a look at some of these craters, high resolution, it'd be very interesting to see what you find.
Going back to another question about narrow wave bands, if you pick some narrow wave bands which match the Clementine spacecraft, the UV-Vis camera, then you can also do sort of mineralogy like Mark's been doing here as well.
Exactly, yes, you can do that. But Clementine wasn't as well optimized for mineralogy as the later missions. The Chandrayaan Lunar Reconnaissance Orbiter, and they have learned from the experience of previous missions, and they are very, very well optimized for mineralogy, and I think better than Clementine. If you look at research into lunar composition, you'll find some papers using Clementine data, but you'll find many more. In fact, the Indian probe, Chandrayaan, that really is the absolute standard for lunar mineralogy, which is a very big feather in the cap because that was their first interplanetary probe. And no, that's the one people really do use their data for studying the moon.
Well, we've had a good discussion on this, and we've learned that the moon is more colorful than it looks. So thank you again, Juan José, for your very brave talk in English. And I'm sure anybody who wants to know more details about it, we can, about your methods, we can put them in touch with you if they want to get in touch with us.
Well, David, there are, as I said, there are 2 papers that have been accepted for the journal, and they're on their way to being published. And there may be a 3rd paper later on.
Good. Well, we'll look forward to seeing those.
Thank you, everybody.
Thank you all.
Thanks very much.
All right.
So, good night, everybody.
Night night.
Good night.
Creo que ya